Okay, so hopefully that started the recording and people got messages about that. And then let me try to additionally share my screen so that we can go through the announcements at the start here. Are folks seeing the screen share? I guess I should put this into a proper slideshow mode here. Cool. Yeah, in this view, it's a little bit harder to tell if we are continuing to have more folks join or not. So I may wait like 30 seconds or a minute and then get rolling. Okay, I think we can get going now. Looks like, yeah, hopefully folks can still hear me while I'm sharing the screen. And let's get started with a few minutes of announcements here. So yeah, this is the June 13, 2024 Rubin Science Assembly. So thanks again to everyone for attending to check out this tutorial. Specifically, we're going to be going through a DP 0.2 tutorial. It's named Notebook 9B within the set of DP 0.2 tutorials, and it's called Custom Source Detection Pipeline. So this is kind of a follow-up to what's called Notebook 9A, where we did a custom COAD using a subset of frames that are used for the production DP 0.2 COAD at a certain sky location. And then today, this is a bit of a follow-up to run our own custom version of source detection on that custom COAD. And additionally, one of the main aspects of this tutorial is that we're using this whole pipeline and pipeline task framework from the LSST science pipelines. So we're building our own detection pipeline and then deploying it, as opposed to, say, just running one Python method or function on an image in memory. So yeah, the agenda is that we'll have a few minutes of announcements. Sorry, looks like I have the wrong tutorial there. It should be tutorial 9B, custom COAD sources. I think we may have a chance to finish a bit early today, which will leave time for some questions. The total time taken up by this tutorial end-to-end, just running the Python notebook itself, is something like 12 or 13 minutes, no more than 15 minutes. And that's under the assumption of not having many people running it at once. So maybe it'll be a bit slower, but still, I think we should have a fair amount of leeway in our timing today. As far as announcements, hopefully folks have heard by now, but the LSSD camera arrived in Chile, which is an extremely exciting milestone for the project and for the community of all astronomers who are looking forward to the Rubin LSST data. Again, there is this, in July, the 22nd to 26th, there's this Rubin 2024 community workshop in Slack in California. I believe registration is still open. It'll remain open until June 21, or if we hit 250 attendees, the cap earlier, then it would close at that point. The Rubin Data Academy is another major thing that I wanted to highlight. So that's coming up just next week. Hopefully everybody is maximally excited about that. A virtual series of presentations, hands-on tutorials, and co-working sessions. I believe registration is still open via the link that's provided in these slides. Maybe I should put the link to these slides in the chat once I go out of screen sharing mode, or maybe someone else can help me with that. The other recent thing is that there's some translations of DB0 tutorials into Spanish, and then in September, there's an LSST at Europe 6 meeting in Spain. So yeah, just a little bit about the schedule of DP0 assemblies for Rubin beyond just this one. So next week, there is no usually scheduled science assembly, which would have been on Thursday, June 20th. Instead, we have the Rubin Data Academy for most of the week. So again, we'd encourage to sign up for that and attend that for all the great content there. And then 2 weeks from now at this time, there will be another tutorial assembly led by Sarah Greenstreet, this time about DP 0.3, rather than DP 0.2. And so this will have to do with near-Earth objects in DP 0.3, which is a solar system-focused data preview. Then lastly, we just wanted to mention, as we usually do in these announcements, that there's something called the Rubin Users Committee, if you aren't familiar with it already. And what they do is sort of like solicit feedback from the community and then provide their version of that feedback to the project itself. And so this is a great opportunity to have your voice heard and to get any feedback that you'd like to get to the project to us through the Users Committee. So let me see if I can stop sharing for a moment while I transition to going into the Rubin Science platform. I'll also see if I can share the link in the chat, just because I know there were some links in there that would be harder or impossible to access without actually having the link to the slides themselves. All right, so now I'm going to go to the Rubin Science platform, which hopefully folks will have an account on, just because in order to really interactively run through things today, you'll need an account there. The other thing to watch out for this time is that you'll need to be using a particular version of the LSST science pipelines. So let me see if I can share that part of my screen now. Okay, so are folks seeing the tutorial notebook in RSP now, hopefully? I guess if not, let me know. So, right, so there's a couple preliminaries here that we need to do before we fully get into running this tutorial. So this, like Notebook 9a, Notebook 9a builds off of intermediate products in the DP 0.2 dataset on the Rubin Science Platform, RSP. And so what that means is that to be compatible with those intermediate data products, we needed to use a particular version of the Rubin Science pipelines, which by now is not quite a couple years, but a year plus, maybe a couple years out of date, called Weekly 2022_40. And so if you're not using that version, then you should follow the instructions here that talk about how to go up to the file menu and save what you've done and log out and then log back in, creating an instance such that you have the 2022_40 version of the LSST science pipelines. So I would encourage you to do that now if you haven't already, just because when you go to one of these relatively older versions of the LSST science pipelines, you're using an uncached image, which means it may take a minute or two to start up, whereas the current latest, greatest version that you would get by default often starts much faster than that. So, right, the title of this tutorial is Detect and Measure Sources in a Custom COAD, and we'll do that specifically by building a pipeline with some of the machinery and building blocks that the LSST science pipelines provide. So as I was saying, it's really important for this particular tutorial to make sure that we have the right version, Weekly 2022_40 of the LSST science pipeline. So let's just go ahead and check that. This is a command where you can sort of issue a shell command from within your Jupyter notebook to check what version of the pipelines you have. And if you see Weekly 2022_40, then that means you can proceed. So it looks like I managed to not screw this up today, and I have Weekly 2022_40 going. Hopefully you do as well, but if not, please follow those instructions right below to get that version going. Okay, so I'm not going to read every single word of the text here, but for those of you who have gone through on your own or through these Rubin Science Assemblies, various of these notebook tutorials that we have for Data Preview 0 in Rubin, you know that one of the first things that we do is to basically just start out by setting up all of our Python package imports. So let's do that now all at once in one cell. A lot of this stuff is very standard, NumPy, Matplotlib, stuff that it's kind of hard not to use when you do anything in astronomy in Python. Towards the bottom, you'll notice a few of these things, lsst.control.mpexec and lsst.pipe.base. These are some of the core pieces of infrastructure that we need in order to build our own pipeline and then deploy our own pipeline through the LSST science pipelines. So while most of this stuff is pretty boilerplate, those are kind of the critical things that we especially need for this particular tutorial. Then there's a couple other sort of preliminaries that you'll often see done in our DP0 tutorials, our notebooks. So here we're going to take the AFW display, that's kind of like the LSSD pipeline's image manipulation display library, and we're going to set it to use matplotlib for compatibility with showing stuff within our Jupyter notebooks. And then, although this isn't the main emphasis of this tutorial, we are going to actually use the TAP service to query DP 0.2 tables later on so that we can sort of compare what we got from our own custom source detection against what is already in the sort of default production version of the data preview 0.2 outputs. Okay, so the first step is to start by finding our custom code in the butler. Now, ideally, one would have run Notebook 9a in order to have access to their version of the custom coad. However, I'm open to the idea that perhaps not everyone has that already run, and so there is a bit of a workaround here that we could do, that you could do if necessary, in order to get access to a readable version of this custom coad, even if you haven't made it yourself. So let me just run the cell as is, as if I were a user who has indeed made the custom coad as part of Notebook 9a. So this is just setting up your username, which is going to be used to find the Butler collection you want. And the Butler repo is DP02, which is kind of a standard thing we do. It just tells us that we're using the DP02 data Butler repository on the whole. So yeah, coming back to the idea of what if someone hasn't run this Notebook 9a tutorial yet, there is a little bit of a workaround that we could do here, which is that you could actually put in my username, because my outputs, which I have run and generated in the past, are available and readable by everyone the way that the Butler currently works on RSP in our current DP0 era. So you'll see my username in a moment, but it's just AMEISNER, all lowercase. So again, if you need that workaround, you haven't run Notebook 9a previously, that's not a concern. All you would need to do is replace getPass.getUser here with a string that's hard-coded that just says my username, and you'll see that again printed out in the outputs here in case you didn't get that just now. So we'll start out by creating a temporary butler that's just going to be used to identify the custom coad that we want, make sure it looks the way we want, in particular that it has the right number of input visits, where visits is kind of like another word for exposure, although they're not quite exactly the same. So let's just print out what collections exist for this user. You can see that I've been kind of very interested in running a lot of Butler stuff here, so probably most folks will not have such a long list of stuff they've run, but if you have run Notebook 9a previously, then you'll want to look for something like custom coad window 1 test 1, which is kind of the search string that we're going to key off of here. So if you haven't run 9a, or for some reason you don't see that custom coad window 1 test 1 collection within your outputs, then you could take my username highlighted here and replace that with for the my username variable instead of getting that from the getPass module. Okay, so anyway, we've checked that, at least in my case, I have a bunch of outputs already, so we can delete this temporary butler. And then now let's go ahead and fully define our input collection. So that's just a combination of this my underscore username variable, which could either be your username, or as a workaround, you could temporarily use my username hard-coded in here in order to get this to run in real time today. So this is what the collection will look like. Now, within that collection, there can be multiple different what we call runs, which are different timestamp directories of when we had run it multiple times, if you had gone through 9a multiple times like I did. So now let's start by creating a butler that uses this input collection that we've just found. Again, either your own version of custom coad window 1 test 1 or my version by hard coding my username in. And so the way that this butler should work is that it effectively will look in this input collection, so this custom coad collection first, to find things, and then anything I can't find in there, it'll go and look in the more general, broader DP 0.2 Butler repository within the Rubin Science platform. So for folks who have done some of these tutorials previously, especially the notebooks, you'll notice and remember this idea of a data ID, which is kind of like the coordinates or the way of specifying a particular piece of the data within the broader data set. So here, just keying off of data preview 0.2 tutorial 9a, we'll go with that exact same data ID because we only made our custom coad for one data ID, which is an I-band coad. The track number is 4431. There's not really anything special about that, but that's just what it is. And then patch is kind of like the counter within that track number of the smaller subsection of the coad footprint. So let's go ahead and try to retrieve this deep coad with the butler based on the data ID. And now let's just double check to make sure that we really have the custom coad and not some other version of the coad, such as the original data preview 0.2 version. So what we're going to do is we're going to look at the coad inputs and specifically the list of visits. And so our custom coad should have, I believe, 6 visits, which is exactly what we have here. Table length equals 6. If you were somehow looking at the original DP 0.2 coad, the non-custom version, you would get a much larger number, I believe 161 I-band input visits here. And so I don't think that is if you were to be using the original DP 0.2 coad, the non-custom version, I'm not sure that would be a fatal issue for running this 9b tutorial, but it might take longer to run your source detection, for example, because the original version is deeper. It has a much larger number of input visits. So hopefully folks are seeing table length equals 6 here. If not, you might still be fine using a different version, although it could take longer time or shorter time to run the source detection itself, depending on whether you have a deeper or shallower version than this. Okay, so let's move on to running source detection. By the way, I'm holding off a little bit on pausing for questions because there's going to be a natural pause for questions shortly when we actually run the pipeline that we create, because that takes something like 12 minutes. So we'll have a 12-minute hold there while the pipeline is running to discuss anything we want to discuss or have question and answer time. Right, so the basic idea of what we're going to do here is that we want to set up an output collection. So where the outputs of our pipeline, our custom source detection pipeline, are going to go on the RSP. You can think of this as being like the directory that you're going to put stuff in for your outputs if you had a local file system. And then beyond that, in addition to defining the output collection, we're also going to define our own pipeline. We'll see how to do that, and then also run it with something called the LSST Science Pipeline Simple Pipeline Executor. So let's start by creating our own output collection now for these custom coad sources that we're going to generate, the catalogs we'll generate. So again, I have my username in here. I think that even if you had not run Notebook 9a, you could still put your real username in here. You would be writing to your own area. And I believe that also it would be possible to write to my area as well if you want to do that. I think that's just the way things work in this DP0 era, where we have relatively loose restrictions on what is able to be done on the RSP. Okay, so now we're going to create another butler object here called simple butler. And the idea is that this is what we're going to use to actually run, eventually, we'll see later on, the simple pipeline executor object. So we're going to specify for this the butler repository, which is just DP02. It's a standard thing we do on RSP when we're working on DP02. The input collection, which we've already talked about, it could be either from my collection or from your collection if you've run Notebook 9a. And then there's also the output collection now specified, which we just defined one cell up. So let's run this. This should be fast, maybe only a few seconds at most. Okay, yeah, great. And then the other thing we can do to sort of check that what we've done so far makes sense is to look at the chain of collections, as we call it, within the LSST science pipelines for this new butler object we've created. And you can see what we've got here is that the chain of collections, essentially reading from left to right, you have the output collection that we just defined, which is where we're going to write our catalogs that we newly create interactively just now. And then it also points back to this custom coad window 1 test 1, which is the inputs essentially. So that's where we had written our custom coad to begin with when we did Notebook 9a. So having sort of defined the input and output directories, we can now move on to defining the actual source detection pipeline. And so within the LSSD science pipelines, the word pipeline kind of has, or at least it can have, a special meaning, which is, pipeline, you could often use it colloquially to just refer to anything that does a data processing. But within the LSSD science pipelines, pipeline tends to have a specific meaning where it means a specific set of what's called LSSD pipeline tasks that are arranged together in order to form some coherent set of data processing that starts with some input and ends with some output. And to be more specific, the way that pipelines are defined, they're very flexible in the LSSD science pipelines. And so the way that they're defined is via this YAML syntax. So YAML is just kind of like a markup language that you can open a text file in some editor and write a YAML file. You can also look at a YAML file and it's human readable. So the way this works is that you have some YAML file, and we'll need to sort of specify exactly what that YAML file is and how we're going to use it. The approach here is that we're not going to start out with a totally new YAML file. It is possible to start with a blank screen in your text editor and write a YAML file that is a valid LSST pipeline, but here we're not going to do that. The way we're going to start is that we sort of already know the overall steps that would go into creating coads and catalogs and so forth with DP 0.2 on the RSP, because folks already did that to make DP 0.2 in the first place. So instead of starting out with a totally blank YAML file, what we're going to do is we're actually going to start out with the so-called DRP, or data release production pipeline, that was used to make data preview 0.2 itself. And then the trick is that we're not going to run every single step of the data preview 0.2 production data release pipeline. And the reason for that is because we don't want to start all the way from the beginning of processing like raw frames, et cetera, et cetera. We really only want to do a couple of specific steps. And so this notion of bringing in steps brings in the concept of a pipeline URI. So that's uniform resource identifier. You can kind of think of this maybe, to me, it brings to mind the idea of a URL, although it's not the same thing. But anyway, this concept of a URI, what you can do is you can specify the YAML file. And so I've highlighted the name of the YAML file here. Since we've set up the LSST science pipelines, you don't need to manually expand out this environment variable DRP pipe tier. But anyway, that's the full name of the YAML file that defines the actual processing that was run to create DP 0.2. And then there's specific steps that we want to do. And the way that you specify this within the LSST pipelines is that when you create the URI, what you do is you start with the YAML file, and then you add a pound symbol, and then the comma separated list of the specific steps that you want to run from within the broader pipeline. And so here, as I mentioned, the title of this tutorial is Custom Source Detection. In detail, it's actually a list of 4 steps that we want to run within the framework of pipeline tasks and LSST pipelines. So these steps are detection, which makes sense. That's probably the first one you would have guessed. There's an intermediate step called merge detections. And then we'll move on to sort of higher level stuff like deblend and measure. So deblend is basically taking the initial list of sources that were found and then trying to ask, like, are there any overlapping sources, and can we do a better job of apportioning those into a larger number of distinct sources? And then measure is more like, well, we have this nice list of deblended source locations. Let's go ahead and do things like measure the fluxes in the various bands for these sources at these specific locations we found. So let's go ahead and define the pipeline YAML URI. And you'll see here, as I described, it's just the full path to the DP 0.2 data release production pipeline YAML file. And then that's appended with a pound and the list of steps, comma separated, that we want to run. So having gone through that explanation of how LSST science pipelines are defined using these YAML files and using these URIs to access specific steps with them, it's actually quite easy to just now make our pipeline. And the way we do that is this pipeline.from URI invocation here. So now we've defined our pipeline at a basic level. However, in the spirit of making this truly a custom pipeline, in addition to running on the custom coad, let's also gain some experience now and configure certain aspects of the pipeline in ways that suit what we want to do. So if any of you have ever had experience, perusing or perhaps using pipeline tasks from the LSSD science pipelines, you'll know that generally they have quite a lot of configurable parameters such that it's not like a one-size-fit-all of running the pipeline. You can really configure like all these different details of exactly what parameters you set within the tasks that are run. And so here we're going to do some examples of that through doing this method called add config override on our custom pipeline. So the idea of override just means you're going to take some parameter of the pipeline task and you're going to specify a non-standard value for one of its configuration parameters. So the way this method works is that the first argument is what step of the pipeline you're trying to configure. So here you see examples of detection, deblend, and measure. And then the second parameter is the specific, the second input to this method is the specific parameter within the configurations that you want to change. So in the first example, the first line here, what we want to change is the threshold value. So this is kind of like how many sigma you want a source to be in your detection map on the custom coad in order to call it a detection and then to do all the follow-on steps like measurement and deblending with it. So here we're this isn't a general purpose recommendation, but here for multiple reasons, including the fact that we want this to run relatively quickly, we're setting this to a higher than default value of 10. So essentially what we're saying in combination with the second line here of the threshold type being standard deviation is that we want a source to be detected at 10 sigma in the detection map in order for us to catalog it in our custom source catalog. The third line here is sort of about how many times you let the deblender iterate its process of trying to separate out sources from one another. Off the top of my head, I can't recall what the default value is here, but generally we want to choose this to be a reasonably low value so that, again, it doesn't take an excessively long amount of time to run this, especially given that, you only have half an hour left. And then lastly, there's this do propagate flags false. That's not too important. It's just that here we don't really need to propagate any information about which sources were used for PSF construction. So I wouldn't dwell on that, but it's just something about the data workflow here. Okay, so that ran just fine for me, hopefully for other folks. I'm not going to go into this in too much detail, but generally speaking, when you run a pipeline on a set of data with the LSST science pipelines, it's very useful before you actually go and just run stuff on a bunch of data to try to look at something called the quantum graph. This is a tool used by the LSST science pipelines to visualize the sort of workflow of how you go from some input set of data to some eventual output set of data. And you can see all the different intermediate data products that are created. So those are the data products are the light rectangular boxes with rounded edges. And then the actual pipeline tasks, the things that sort of do the processing work, are the darker rectangles that have square edges or right angle edges, I guess you would say. And so here is a quantum graph that I generated for this specific custom coad pipeline. If you look down a little bit here, you can actually find the commands. If you'd like to run them themselves, there's commands that you can use to create this quantum graph yourself if you're interested. I'm not going to do that explicitly here, but if you want to, you're welcome to. So the basic idea is that the way you read these quantum graphs is you start from the top and you go to the bottom. And then the arrows indicate sort of the flow from input data to pipeline tasks to then the output data of those pipeline tasks. And so you can see at the start, at the very top here in ours, we're starting with deep coad. Remember, deep coad is just a name that's used for standard LSC pipeline coad outputs, even though the custom coad we made is actually shallower than the normal DP0.2 coad. Then the first thing you do is detection. That creates several outputs. Then you go into the merge detection step. which also creates a couple of outputs. Then you go into the deblend step, which creates looks like five, or yeah, it looks like at least a couple outputs. And then lastly, you go into the measure step, and the measure step is what outputs the final catalogs that we'll inspect and like look at the fluxes and magnitudes of objects in. Okay, so yeah, if we can hold questions for just a couple minutes, it would be great if we could get to the part where we actually deploy the source detection pipeline, which takes maybe 12 minutes or so if things are going well. So we're pretty close now. We've defined our pipeline, which is great. We've defined our input and output collections, which is also nice. The other really critical thing we need to do is define a query string. And that's because if we don't define and specify a query string, then we would effectively be telling our processing to process all of DP 0.2, which is not something we necessarily want to do. I don't, especially not in this limited time frame, but I would guess just in general, we also don't want to do that for a variety of reasons, including it taking a long time and creating a large volume of outputs that is really not the intention to support on a per user basis. So let's define the query string. You've probably seen these before in different contexts if you've ever done any of the tutorials using the butler. But you can kind of think of this as another way of specifying your data ID, right? So again, we have the track number or the patch number. The band is I-band because that's the band we made our custom coad in. And the last thing, which maybe you might not have guessed, is SkyMap equals DC2. So DC2 is just the name of the simulation that was run by Desk in order to create DP 0.2. So this is the query string that tells us to only look at our custom coad rather than trying to process the entirety of data preview 0.2, which is definitely something important we want to capture here. All right, so the next step, now that we've defined our pipeline, as we talked about with the YAML and the URI, we've defined our query string to only be the custom coad and not the rest of DP 0.2, and we've created our butler already with the input and output collections. Now it's just one command to create the simple pipeline executor object. So we'll do that now. This doesn't actually execute the pipeline yet. It just creates the pipeline executor. I would not worry about that warning. Yeah, I mean, it says explicitly here, the command generates a warning message that can be ignored. Okay, so now we get to the real sort of meat of this, as long and in the sense of how long things take to run. So this quanta equals spe.run command is essentially just calling the .run method of this simple pipeline executor object we just created. So let's start this. I guess we'll see if there's any slowdown from the fact that we have multiple of us trying to do something very similar on RSP at the same time. Just going to make a note of when this started for me, just so that I can have a sense of whether this is running on schedule or not. So this is going to take about 12 minutes, and it should, over the course of those several minutes, be printing out several logging outputs. Let's see if it starts soon. Right now, for me, I haven't seen any. Oh, yeah, I have some. Hopefully, folks are seeing that appear as well. There's some instructions right here about making these logging outputs into a scrollable inset window, which can be nice. I think for whatever reason I'm using a Mac, but I'm using Chrome. Maybe it's browser dependent as well. But for me, I don't think I need to generally do that. But anyway, you'll see that now as you're running the pipeline, you get these different printouts, and to me, at least, I would say these printouts make pretty good sense as far as what I would expect to be happening. I'm going to take another 10 minutes or so, so I think we can take any questions now, since we have a little bit of spare time built in here. If anyone wants to ask any clarifications about what we've talked about so far. I know this is a relatively technical tutorial, and it is classified as an advanced tutorial. So yeah, I would totally understand if there are any questions out there about specific aspects of what's been done so far, or where we're going with this. So, spam call. Okay, well, not hearing or seeing questions yet in the chat. You can see now that we're starting to get, at least I'm starting to get some printouts that say things like deblending 2669 sources in one exposure. So that makes good sense. To be honest, I don't exactly know in what order everything gets run, right? Because that's kind of the point of these quantum graphs, is that it sets everything up in terms of the inputs and the outputs, and then you don't need to worry about exactly what order things get run in. Clearly, there's some level of things being able to run. Well, maybe there's not really in this case because we only have one patch, but in many cases there is some element of things being able to run themselves in parallel. I think in this case, deep blending may be the sort of plurality of the time here. Is that it may be the longest amount of time of any of the steps, the 4 steps we mentioned. Yeah, Brian, I see your hand is raised.
Yeah, thanks. So is this, I might have missed, is this doing detection on like one band or is it doing all six at once? Or how does that work?
I believe it should be doing detection only on one band, and that's just because of the way that we gave it this query string of where band equals I, etc.
Ah, okay.
So I believe that's essentially the entire answer there. And we'll
Mm,
see that in the outputs that we can tell that it's not analyzing all the bands because this is a shallower single band coad
mm,
that we're analyzing. And so actually we detect fewer sources than we would if we were looking at the full depth I band coad, or if we were looking at all the bands together.
sure.
So we'll see that later.
Yeah, yeah. I was thinking, if you wanted to do like, okay, say a lower threshold, like, it's only got to be five instead of 10 or something, but you want it to be that in at least one band or at least two bands or something, how
Mm.
you kind of if you
Yeah.
can do the bands and then blend them, what would I say, cross-reference the catalogs that get created or something, yeah.
Yeah. The other thing is, I believe we didn't do this here. I don't know if we tinkered with any of the Blender parameters. Oh yeah, we did the max iter. Um, but I believe if you wanted to get really into the configuration parameters for the deblender part of this, I believe it would be possible to make it such that you do the detection on this custom I-band coad, but then you do the deblending in a multi-band way that accounts for all the coads in the different bands, including your custom I-band coad and
Mhm.
the other band coads that would be drawn from the remainder of
Yeah.
data 0.2. Off the top of my head, I don't know if I could recite for you exactly which configuration parameters you would change, but I believe that is possible by doing more of these
Okay.
config.
Okay. Cool. Thanks.
It looks like I'm now in the measurement phase here, right? Because the bottom printout I have is about measuring 5603 sources. So to me, this all seems like a fairly good sign, although we probably still have something like 5+ minutes left before we totally finish here. Is anybody's pipeline running at a significantly different rate of speed than mine, or are we all at pretty much a similar place of being in the the measurement step of this pipeline? Did anybody actually try creating the quantum graph themselves? How did that go? Or did no one try it? Okay, well, in the absence of other questions, I can start to, in the interest of time, although I think we're doing fine on time, to be honest. Uh, we can start talking about a little bit what we're going to do in the later parts of this tutorial. So really the sort of important, unique part of this tutorial is what we've already covered so far. But in the latter part of this tutorial, we're going to go through some stuff that's perhaps more reminiscent of the things you've already done more and more so in the past with the RSP and specifically the TAP service and being able to query the catalogs from DP 0.2. And so the reason we're going to be doing some of that DP 0.2 catalog querying is that we're going to be comparing what we got in our custom coads with our custom source detection pipeline to what's in the sort of default production version of data preview 0.2. And so that's going to start out with a couple commands that are reading back the outputs that were written out by the butler from this simple pipeline executor run command that we just did. And then the second aspect of that is that we're going to issue some, I believe, just one query to the TAP service in order to get the corresponding list of DP 0.2 sources over the same footprint in I-band with the same detection threshold of 10 sigma. And then we'll make various plots. We'll convert the fluxes from our custom source detection run into AV magnitudes, and we'll make various plots, like comparing the magnitudes from the DP 0.2 TAP query to our own magnitudes from our custom catalog, and then also looking at, for example, the spatial distribution of where these sources land, and just like an overall histogram of the I-band magnitudes of the recovered sources. So let's just check back in with what's going on here. It looks like to me it's all still running just fine. I would guess that we have maybe 2 or 3 more minutes left before we finish running. Has anybody's been like 1 sigma faster than the rest of us and finished, or no? Yeah, there are a couple warnings here that I'm seeing, but yeah, as we say here, there will also be a couple of warning messages which can be ignored, so we should not worry about that for now. Yeah, so this is a nice illustration of why it's actually useful that we made a relatively shallow coad, because I assume that all of this would take longer if we had gone with an even deeper version of this I-band coad. So, and if we had not overridden the parameter for setting the source detection threshold to 10 instead of 5, then presumably this would also be taking longer. Oh, mine finished. Has anyone else's finished? Well, in any case, in the interest of time, I'll probably go on, but yeah, hopefully other folks' pipeline runs will also finish or have finished already. So as I was saying, the next step is to analyze the custom source catalogs that we just created now. And so, you can think of this as we just wrote some new catalogs to disk on our file system, although, this is actually a little different than that. It's in the cloud. So let's go ahead and read in our source catalog. So The way you do this is with the butler, right? In LSST, we don't specify specific names of FITS files or anything like that. We specify our collections to the butler and let the butler, deal with under the hood all the details. So let's go and get the deep coad measurement catalog is what it's called here. The reason for that is that's kind of like the highest level catalog we have. It's the one that has the source locations that we found through all of the detection and deblending, but also the fluxes that we measured at all those locations. So I think this maybe takes like 5 seconds at most, I would guess. Yeah. Here's just a little bit of reformatting for convenience of the source table. Don't need to go into details of that. There's a couple optional things you could print out, like, what are the column names of the catalog I just created, and look into that a little bit more. The other important thing to do, though, is to add some magnitude columns, so some I-band AB magnitude columns to our newly created catalog. Generally speaking, LSST uses fluxes for various reasons, like you can have negative fluxes sometimes, and what do you do with that for magnitudes? So we need to convert to magnitudes ourselves here. This is not entirely dissimilar from how you have a function to do this conversion within tap queries sometimes, and I think we may even see that later on. So here we just computed the AB magnitudes from the fluxes we measured based on this get photo calib of our custom deep coad. So this is an object that sort of holds some information about the 0 point essentially in our custom coad. So now let's also restrict to primary equals true sources. This is something you've probably seen before if you've gone through any of these tutorials. We don't want the so-called parent sources here for our production analysis we're about to do of plots and so forth. And we also don't want things that are right near the coad image edges within our custom coad. So let's first off just make a histogram of our AB magnitudes in the I-band that we got from our custom coad. And this is what it looks like. We'll do a comparison later to put this in context with what it would look like for the deeper version that you get from the original DP 0.2 catalogs themselves. So now the next step is it would be nice to actually look at where these sources land within the image rather than just look at their histogram in abstract. So let's do that. The first thing we're going to do is make a cutout from our custom deep coad in I-band. And then, we're going to do some manipulation with the WCS of that cutout and look at the central RA deck. And so if you were to compare the central RA deck to what we talked about in Notebook 9A about the idea of looking for a supernova precursor at this exact RA deck, you'll see that this all makes good sense together. And then let's convert the supernova coordinates to pixels so that we can also plot that on our overlay in a moment. Again, this, I won't go into full details here in the interest of time, but these code cells here demonstrate a bunch of useful functionality as far as common things you might find yourself doing eventually with LSST data of like converting between world coordinates and pixel coordinates and coads and so forth. So now let's display the cutout with detected sources as orange circles. This goes back to the question that Brian asked earlier. We'll see in a moment, especially when we overplot both our custom coad with its sources as well as the original coad with its sources. So here's what it looks like. It's, of course, so the green circle, I believe, is the location of this hypothetical supernova that we were looking into, which is the reason we made these custom coads in the first place. And then the yellow circles are showing what we detected at 10 sigma in our custom coad. So it's certainly encouraging to see that, first of all, this does look like a reasonable image of the sky with some galaxies and some point sources in it, and also that the 10 sigma source locations do line up overall with where we see the sources. So that's all very encouraging. Let's clear up some memory a little bit by deleting some objects that we no longer need going forward. And then the last part of this tutorial is just to compare what we got from our custom coad, which is actually shallower than the original DP 0.2 coad with the original DP 0.2 catalogs. So let's start out here by making a temporary butler. The reason we do this is because we want a butler that only looks at the DP 0.2 collection, not our custom coad collection, right? We don't want to just accidentally retrieve our same custom coad and compare that to itself. We want to look at DP 0.2, the original version. So that's why we create this new butler with this only one collection. That's the sort of production DP0.2 collection. Now let's actually get that deep coad from data preview 0.2. This may take a few seconds. Going to repeat what we did earlier, but we're going to do it now for the original coad, and we should see something like 161 input visits. That will tell us that we indeed retrieved the deeper original version of the DP0.2 coad. And that's great. We do in fact see that we have a deeper version of the coad from the original DP0.2 with a larger number of input visits. So now we can delete the temporary butler since we have used it to get the original DP0.2 coad that we needed. And then here's some manipulation of the DP0.2 coad in order to build a cutout. So I won't go into full detail on all these functions, but they're very useful parts of the LSST science pipeline that you could imagine using very frequently in the future with real LSST data. So right, as I mentioned previously, we are going to now retrieve some of the DP0.2 catalogs via TAP query because that's the sort of the best way we can do to compare what we got from our custom source detection pipeline to what's in DP0.2 itself. So here's the query. I won't go into full details, but as I mentioned, just like we in our Python notebook had to convert our custom catalogs fluxes into magnitudes, so too this query also converts I-band fluxes into magnitudes. The other important thing to notice about this query is that we're making a signal to noise equals 10 cut here where I've highlighted, and that's for the sake of making a fair comparison, right? It wouldn't be as fair of a comparison to let all the sources down to 5 sigma into this TAP query because we explicitly said we only wanted 10 sigma sources in our custom source detection pipeline. Okay, let's just reformat this table now into pandas, which is slightly more convenient to work with. And then right, again, because we want to overlay these DP0.2 source locations onto our cutout of the original deep coad, that means we need to do, again, some of the same utility function stuff in order to go from sky coordinates to pixel coordinates in the deep coad cutout. All right, so now we get to really see, kind of like the end of the story here or close to it as far as the comparison between our own custom source detection on our custom coad versus what's in the sort of production version of data preview 0.2. So let's go ahead and make a side-by-side plot where we show the two different coads, the shallower one that we made ourselves with its 10 sigma sources, and also the deeper coad from DP 0.2 with the DP 0.2 sources. I don't think this will take more than a handful of further seconds here. So yeah, here we go. So on the left, we see the same plot we made earlier, but a little smaller. Basically, that's our custom shallower coad with its 10 sigma sources that we detected from our pipeline. And then on the right is what you get from the data preview 0.2 sort of full depth. So you can see there are more sources right in the version on the right with the red circles, which makes sense because there were, something like 20 times more input exposure time total for that coad. So just the last couple of comparisons here, it would be good to check custom source detection on our custom coad agree reasonably well with those that were found from the original DP 0.2 itself. So let's go ahead and try that. By now we have, we've read in from the Butler repository the outputs that we just created, and we also did the TAP query to get the magnitudes for DP 0.2. So this is just a matter of plotting pretty much. And you can see that you have, I-band magnitude on the x-axis, and then the custom I-band magnitude on the y-axis, and the black line is y equals x. And indeed, you see things falling along that line with some scatter. There's multiple reasons you could imagine for the scatter. One is just that at the faint end, we have less data, and so you could imagine it being noisier in our custom coad. And of course, the other one is that there could be different deep blending of sources, the way we've done it here, where we did sort of single band deep blending on I-band versus what was done for production of DP 0.2 itself. And then the last plot we'll make is just another sort of check to understand that what we've done makes sense. So we'll look at the comparison of the histograms of apparent magnitudes that we've got from our custom source detection on our custom coad versus what's in DP 0.2 itself. And you can see here that the result, at least qualitatively, makes sense. So what you can see is there's a lot more sources detected in the original deep coad, which is just a function of the fact that it incorporated a lot more exposure time, a lot more visits. And then the other thing you can see is that the magnitudes cut off a little bit brighter here for our custom coad, the blue compared to the orange, which also makes sense because of the fact, again, that we just have a shallower custom coad than the original deep coad. So with that, I think we can pretty much leave the last 4 minutes, I guess, for questions. There are these interesting exercises for the learner. One would be to try lowering the detection threshold in our custom pipeline, say from 10 to 5. And then you could remake. You would also, I expect, find that the pipeline takes a little bit longer to run than it did previously. Other things you could do are compare things like the shape parameters in the catalogs rather than just the mags. And then you could also try what we call this window 2, which is a different set of visits. So you can make a new custom coad with a different number of visits and then rerun all the same machinery, the custom source detection, but on that different coad that you've generated. So with that, we have a couple minutes for questions if anybody wants to ask anything or raise anything for discussion. Thanks, Bob. For some reason, Bob is the only one I see on my screen the way that Zoom is doing this. So I don't know if anybody else is making gestures or not, but okay, well, not seeing any questions. I guess I'll just make one last shout out to the fact that there's this, oh, sorry, wait, I see something in the chat. Oh, my notebook is still running. Yeah, Sylvie, I'd be curious to know about some of the printouts that you saw earlier about whether it was indeed getting the a custom version of the coad that only had 6 input visits, or if somehow Butler was finding the deeper version that has a much larger number of visits. That would be my first guess as to why something would still be running, is that it's running on a deeper version of the coad. Okay, interesting. Are you my only, okay. So that was one guess, which was wrong. But my other immediate guess would be that have you checked the size of your container, that it's large rather than medium or small? Okay. Yeah, I wouldn't expect it to be a problem of having just run the first notebook today. That's interesting. Yeah, so my first two guesses would have been running on a deeper version of the coad or running on a smaller container. Does anybody else have any guesses as to why one person's version of this notebook might take longer to run than another? I don't. Beyond that, those are my two sort of obvious guesses, which it sounds like weren't correct. So I'm happy to open it up to other hypotheses here, but those were kind of my first two. I mean, this is all running in the cloud, and we were doing something unusual of trying to run essentially the same thing with multiple people all at the same time, which isn't necessarily something that's always being done. Even when we have the real LSST data in the future, it's to me, it seems a bit unlikely that lots of people will be trying to run exactly the same processing at the same time, given that there will be lots and lots of data. So, you can imagine sort of randomness going on here with the cloud resources and the fact that we're all hitting the same resources at the same time. But if anybody else has hypotheses about why one person's would take much longer than another. Yes, well, yes, I should have actually asked that. It's good that you are at that line, the quanta equals spe.run, because that at least makes sense. That's the part that should take a relatively long time. But as to why one person's would run longer than another, I don't. Yeah, I've given sort of my main hypotheses that come to mind. So With that, I think we should probably stop recording since we're at the hour. I don't let me stop sharing first so that I can hit the stop recording button. Where is the stop recording button?